Welcome back. So I'm really excited to do this lecture on reinforcement learning. I've been wanting to do this for a long time. Those of you who know me know that I love control theory and machine learning, and reinforcement learning is kind of at this sweet spot between these two super important fields. Okay, so reinforcement learning is essentially a branch of machine learning that deals with how to learn control strategies to interact with a complex environment. Okay? And so one of the ways I think about this, the way I'm going to define this, is that reinforcement learning is a framework for learning how to interact with the environment from experience. This is a very biologically inspired idea. This is what animals do. So through trial and error, through experience, through positive and negative rewards and feedback, they learn how to interact with their environment. Okay, good. So before I jump in, I want to show some motivating videos. I really like this one, where reinforcement learning is used to learn how to walk in this artificial environment. And there's a lot of papers like this where people use reinforcement learning as kind of an optimization framework to learn how to control a complex system, in this case a bipedal walker, often in a simulated environment. And this just looks really cool. And it's a difficult control problem. This is a really hard nonlinear control problem. Now, the goal would be to take what you learn here and start to port that over into the real world to make better robots and better actual physical agents that can interact with the world alongside us, to learn how to learn like humans and animals do. So another video I love, this is my dog Mordecai, and my wife has trained him, this is a treat on his nose, to hold the treat on his nose until she says okay, after which he can then grab the treat and eat it. This is not an easy trick to learn, and this, again, this goes to show you anytime anybody who's trained an animal, a dog or any other animal, has done some type of reinforcement learning or reinforcement training, okay? And so that's actually where the word reinforcement comes from, is that in animal systems, in human systems, you reinforce good behavior with rewards like treats. Okay, and so that's kind of the whole name of the game here, is learning a good control strategy or a good set of actions through positive reinforcement. Good, so that's what we're going to talk about today. I'm going to walk you through the framework. So I want to disentangle, there is a reinforcement learning framework, kind of the framework for how you learn to interact with the environment. And then there is a hard optimization problem for how you actually optimize the agent's actions or policies given that framework. And those are kind of two pieces that we're going to talk about today. And then in a future video, I'm going to talk about kind of deep reinforcement learning or reinforcement learning with modern techniques and deep neural networks and some of the incredible applications and performance that you can get out of those systems. Good. So also I'll point out you can follow updates on these videos at eigensteve on Twitter. Please like, please subscribe, hit the bell so you get notifications, and comment below. Tell me what you want to see more of. Tell me what you like or don't like. Oftentimes people in the comments provide a lot of really important, useful information that I might have left out of these videos. So I think it's also a big service to other people watching these. All right. So we're going to jump in. And we're going to build this reinforcement learning framework from the ground up, from scratch. And so at the heart of it, you start with an agent and an environment. And the agent, I actually like the name agent because it implies some agency. The agent gets to take actions to interact with the environment. So in the first example, and I'm going to have a few examples, we're going to talk about a mouse in a maze. So the agent is a mouse, the environment is a maze. The mouse gets to measure its current state in the environment, so it measures its state S. Notice that it doesn't measure the full state. The mouse does not have a top-down view of the whole maze. It just knows where it is right now and where it was in the past. And then the mouse gets to take some action A. It gets to make some decision about what to do next. Okay, so it could turn left, it could turn right, or it could go forward in this case. And only until the very end of the maze does the mouse actually get a reward R. So these rewards are very sparse, few and far between. In this case, if it goes to the very end of the maze, it might get a piece of cheese. Actually, my wife tells me that when they do training experiments for rats, they really like Fruit Loops, and it looks adorable because a Fruit Loop is gigantic to a mouse or to a rat. But the moral of the story here is that this agent gets to make some decisions. It has control over its actions, so it has agency. And the environment, it gets to measure where it is in the environment, and occasionally it gets rewards. Very occasionally it gets rewards. And so part of the goal of this system is to learn what actions actually caused it to get a reward or not. Okay? And this is, in some sense, in the machine learning lingo, this is called semi-supervised learning. So if the mouse got a reward at every single stage of the maze, if at every correct turn it got a piece of cheese, that would just be regular supervised learning, and those rewards would be called labels. They would tell you, yes, you did the right thing, or no, you did not do the right thing. But because the reward here is time delayed, it comes at the very end of the game, or very sporadically, and it's not linked to every single individual action, we call that time-delayed label a reward, and this becomes a semi-supervised learning problem. So it's still supervised in the sense that there is supervisory feedback telling the agent what worked and what didn't, but it's not nearly as much information as in classical supervised learning. And that's one of the major challenges of reinforcement learning, is that these labels are extremely rare, and it's very hard to tell what actions gave rise to actually getting that reward. So this is a much harder optimization problem, and oftentimes requires much more data and much more trial and error. And I'm going to talk about that. Good. I also like to think about the game of chess or checkers or tic-tac-toe, basically games in general, where the agent, basically there are some rules of the game, and you get to make a finite set of actions to interact with that environment. Now, in the case of chess, it's interesting because the environment is not just the rules of the game, there's also an adversarial opponent trying to beat you. So you're trying to beat the opponent, you're trying to checkmate the other side, and they are trying to beat you. And so that's really interesting, is that the rules of this game are trying to, there's an active player on the other side in this environment. Good. You also might be a Terminator trying to rule the world or try to learn how to walk. I actually think this one's kind of funny, that in the Matrix, Neo is actually the agent from a reinforcement learning standpoint, trying to learn the rules of the Matrix, which is the environment. Okay, so let's go back to the chess example, because I think the chess example really exemplifies a lot of the issues with reinforcement learning. So we're going to use this as kind of our exemplar problem. At the end of the day, the big challenge in reinforcement learning is to design a policy of what actions to take given a state S to maximize my chance of getting a future reward. That's all that this agent can do, is decide on a policy. Now, this is called a policy and not a control law. For a lot of reasons, partly because the environment is not deterministic, it's probabilistic, and so this policy is also going to be probabilistic. Okay, so my policy pi, given a state and an action, basically it tells me what is my probability of taking action A given that I'm currently in state S. And again, this is probabilistic because I might decide on playing a mixed strategy. A normal control system like swinging up a pendulum on a cart, the rules never change. The system is always given by F equals ma, and so my control law also is deterministic and never changes. But in the game of chess, maybe my opponent's kind of random. So maybe I'm just learning how to play. So what I'm going to do with my policy is maybe 80% of the time I'm going to move my pawn, this way, but 20% of the time I'm going to try this other move, just in case my environment changes, or just in case, something different happens that time. So you're going to use a probabilistic policy to explore and optimize the rewards coming from your environment. Good. And you get to take actions A. That's the whole point, is that once you have this policy and you know what is the probability of taking an action given a state. And then you just run that policy and you see how much rewards you get. Good. And this all happens in time. So you take actions at time step 1, time step 2, and so on and so forth. You measure the state at time 1, time 2, time 3, all the way up to ST. And there are rewards that you could be getting at each of these actions and each of these measurements. Now, most of the time, these are going to be null or empty. You're not going to get any rewards until maybe the very end of the game of chess. But in principle, you could get rewards at some points along the way. And again, the game of chess is a really good example of how hard this is, because you might create a policy of what you think is the right thing to do in chess to beat your opponent, but you only get one reward at the very end of the game. Maybe I played a great game of chess and I made one mistake and I lose the game. Do I throw away that whole sequence of actions? How do you figure out what actions were good and what actions were bad? That's a very, very hard optimization problem, and that's at the absolute heart of reinforcement learning. Okay, so part of helping design a good policy is understanding what is the value of being in a certain state S given that policy pi. So once I choose a policy, I can start to learn what is the value of each state of the system, of each board position in chess, for example, based on what is the expected reward I will get in the future if I start at that state and I enact that policy. I'm going to say that again. That's a mouthful. So the value of a state S given a policy pi is my expectation of how much reward I'll get in the future if I start in that state and I enact that policy. And there's this gamma to the t, which is a discount rate. And so what this is saying is that I am slightly discounting my future rewards compared to my immediate rewards. So gamma is a constant between 0 and 1 that basically tells you how much you favor getting a reward right now versus far in the future. And this is, intimately related to economic theory, psychology, that, generally people are more eager to get a reward now than wait for a delayed reward much later, okay? But the basic idea is that you can start to understand this policy and what policies are good or bad based on what are good board positions, what are good value functions. And this kind of is how a human would play, is that the set of all states of a chessboard is combinatorially large. There's too many to count. You could never hold them all in your mind. But we start creating rules of thumb of what are good board positions. So for example, if I take my opponent's queen, but I still have a queen, I probably have a better expected chance of winning and getting a reward. And so you might just count the points on the board, and that would give you some proxy for the value of a given state. That's one very rudimentary value function that you could use. And over time, as you play and gain mastery, you might refine your value function and get a better idea of kind of what matters in the game, okay? And that's also then going to help you refine your policy to get to those good states. Good. So in this large framework, again, this is the reinforcement learning framework. The goal is then to optimize your policy to maximize your future rewards. So at the end of the day, it's an optimization problem to solve for pi. So usually we think of our environment as not being fully deterministic like we do in classical mechanics and classical control systems often. And instead we think of our environment as being somehow there's a random or a stochastic component. So these are called Markov decision processes, MDPs. And what that means is that if we are in a state S now and I take an action A now, there is some probability of me going to a new state S at the next time step. And I could go to multiple different states, and it's kind of you roll a dice and you go to that next state. Okay, so I actually think about backgammon. I think that's a great example of a game that it has rules, it has a deterministic element, but at every turn you're rolling die, and that gives you this kind of random Markov decision process. So there's a probability of going from my current state and action to the next state S. And that, again, that makes it hard to optimize these policies, and that's why these policies have to be probabilistic in nature, because your environment is probabilistic in nature. So the credit assignment problem I've mentioned before, it's this idea that because your rewards are often very sparse and infrequent, it's very hard to tell what action sequence was actually responsible for getting that reward. This issue was recognized as early as the 1960s by Minsky, and it's been one of the central, it's the central challenge in reinforcement learning, and it has been for 6 decades. This is the problem that people are still working on today, is how to beat the credit assignment problem. And so a couple of keywords I think are important are dense versus sparse rewards. So again, the game of chess has very sparse rewards. You only know if you win when you checkmate or when you are checkmated, and you don't necessarily get concrete rewards at intermediate intervals. If you had denser rewards, if you were playing with a more knowledgeable master, and they were telling you move after move, oh, I wouldn't move that because then I'll do this, or oh, that's a really good move because that makes this structure that's a really strong, position. They would be giving you extra dense rewards, and they would be helping you learn faster. But in general, if you have sparse rewards, then reinforcement learning is very sample inefficient, to use machine learning terminology. Meaning, if I only got sparse rewards, I would have to play many times. I'd have to have tons of examples to learn a good optimal policy given those sparse rewards. So sparse rewards and the credit assignment problem make it very hard to learn through optimization what the right policy is. And that's related to sample efficiency. So in general, what we do in a lot of systems is called reward shaping, where even if you get an infrequent reward, an expert human might build a proxy reward so that you get more dense intermediate rewards on the way to this final reward. And so an expert human would basically guide the learning process by giving more dense rewards intermediately. That's called reward shaping. Okay, good. So now we're going to talk about how, again, the ultimate goal is to optimize this policy. So there's lots and lots of strategies for this optimization problem. And remember, I'm going to go back and say all of machine learning and all of control theory almost are optimization problems. They are, you can pose these as hard, nonlinear, non-convex optimization problems. And then in the case of machine learning, you solve them with data. Okay? In the case of control, you solve them subject to the constraints of the dynamics. This is no different. This is at the intersection of machine learning and control theory, and reinforcement learning is, again, a big optimization problem within this framework. And so to optimize this policy S and A, given measurements of your rewards, given this sporadic feedback, there are lots of strategies. So there's differential programming. So reinforcement learning and game theory kind of grew up together, and differential programming is one of the optimization techniques. Monte Carlo is an old strategy for optimizing these policies. Just try a bunch of stuff, kind of randomly. Temporal difference is like an optimal balance between differential programming and Monte Carlo, so it kind of finds the sweet spot of both of these, and it's model free, so it doesn't require you have any model of the system. And it's related to the Bellman optimization. So Bellman was one of the pioneers of optimal control theory and also laid a lot of the foundations that are used in reinforcement learning today. Now, in the reinforcement learning problem, and this is true, again, for most of machine learning, is that there's this balance, and control theory for that matter, between exploration and exploitation. So this policy, pi, usually we're going to parameterize this. We're going to have some parameters. We're going to try to optimize those parameters to win the game, to get the reward. Now, how much effort, how much do I put into optimizing a strategy or exploiting a strategy, and how much effort do I go to try new things that might not work, but might also give me better rewards, things I've never tried before? How much effort am I going to use to explore good policies versus to exploit a policy I think is the best one? And this is always a challenge. I'm not going to talk too much about this. I talk about this a lot in other videos, but this is a fundamental challenge in machine learning and control theory, is this exploration-exploitation balance, and it's a big problem in reinforcement learning also. Policy iteration is, so basically you set up a dynamical system where, based on your rewards, you iteratively update the policy to make it better and better over time based on new information, based on better information from new rewards. That's policy iteration. And there are lots of strategies to do this. So I'm just going to name a bunch of them. So you can use simulated annealing, evolutionary optimization, gradient descent, and you can use all of the modern tools in neural networks and machine learning, stochastic gradient descent, atom optimization. So a lot of really interesting new work is happening just in the last 10, 15 years using deep learning to optimize these policies. Okay, good. So I'll just give you some cool examples. So this is one of my favorite examples of learning how to catch a ball in a cup. This is a fun kids game. And so an expert human first off gives the robot like one example to show that it's possible. And then after imitation learning, the robot gets to, through trial and error, notice that there's a white screen and the cup is blue and the ball is red. So it's using visual information from a camera. And after a few iterations, it's actually getting pretty close. I think this isn't so different from how a child would learn. You know, a kid's not going to learn this in 2 trials or 3 trials. It might take a few dozen times before it actually gets close and then learns how to catch the ball in the cup. After 45 trials, it's getting very close. It bounced right off. I don't know if it'll get it at 60. I think it barely misses. But it's getting very, very close after 60 to catching it in the cup. And finally, after 100 trials, the system has actually learned the rules of the game, the physics of how to get that ball in the cup. Very simple robotic example, but it's also pretty interesting. I mean, this video is not that recent, but very interesting to show that it is possible to learn a real physical system. This is another example I love. This is called the Pilko learner. I encourage you to go read all about Pilko. In this case, they're learning kind of how to swing up and stabilize a pendulum on a cart. And again, they are using some combination of trial and error and a physical model to, learn how to do this very efficiently with very few samples. So you couldn't learn how to do this without learning a model or without having a model of the physics, Newton's laws, F equals ma. If you actually, I tried this. I downloaded some code in MATLAB and played around with this just to learn if you could swing up a pendulum. It took like 8 hours on my laptop and thousands and thousands and thousands of trials. Very sample inefficient to learn like the random control signal that gets you near the upright position where you can start to stabilize it. So a lot of trial and error if you don't have a model. So the Pilko learner, in some senses, is leveraging the fact that there is physics. We do know physics. We do have models to learn this much, much faster, much more efficiently, many fewer samples. And I forget which trial we're on, but after trial 5 or 6 or 7, it actually does learn how to get this thing up and stabilize. I think trial 6 is going to get really, really close. Let's see. All right, so and notice that a human does have to get this thing back down to 0. The human's guiding this process all along. All right, so in trial 6, it's going to get really close and almost do it. And I think in trial 7, it's actually going to figure it out. You're going to have to go watch the video to see what happens. Okay, so again, this is our framework for learning. We're trying to optimize this policy. One last thing I'll tell you about is Q learning. So instead of just learning the policy and the value function separately, in Q learning, you can kind of learn them both at the same time. So there's this Q function that's not just a function of the state S, it's a function of the state and the action, and it tells you what is the quality of being in that state and taking that action. So it kind of combines the value and the policy. You can almost think of it as like a value function of the state and the action, assuming I do the smartest thing in the future that I can, the best thing in the future. And so I'll walk you through what this could look like. So the way that you update this quality function is you take your old quality function, and then when you get a reward, you basically update. This alpha is a learning rate. Gamma, again, is the discount rate. And what you're doing, this max A of Q in the future basically says, I'm assuming that I'm always doing the best thing I possibly can in the future. And if I do the best thing in the future, kind of what is the quality of my current state and action? So I'm gonna say this again. This is it almost seems a little circular, but it's a really nice way of combining the policy and the value into one function that you can learn. And again, you can learn with this with a deep neural network nowadays. It says, given a state S and an action A, and assuming I do the best thing I can in the future, what is the quality of being in that state and taking that action? And this is really nice because if you actually know the quality function, then once I find myself in a state S, I just have to look across all of the actions A and pick the one with the best quality. So it's a really nice way of choosing an action given this quality function. When I find myself in state S, I just pick the action that gives me the best quality and I enact that action. And if I do that in the future, I will maximize my value and that gives me a policy. So that's really cool. Okay. I guess another thing I think is super interesting is Hindsight Replay. So again, when we talk about the credit assignment problem and the sparse rewards problem, in that inverted pendulum example that I ran in MATLAB, it took a really, really long time before this thing actually got near the upright position where it could start getting rewards. And so what you do in Hindsight Replay is instead of throwing out all of the data that doesn't actually get you a reward, what you do is you say, maybe my system, my set of actions would be good for a different reward. So maybe in that ball in a cup example, instead of, if I didn't get the ball in the cup, maybe the ball went over here. what I do is I look back, I replay that event, and I say, well, maybe someday I'll actually want to do this other thing that I just did. So I better remember that, and I would encode that that was a good action sequence for a different reward structure. Not the reward I want of getting the ball in the cup, but this other reward of getting the ball over here. And then by learning how to get into these different states, you get a lot more reinforcement, a lot more like kind of artificial rewards, and you learn more about the physics and the dynamics of the system, about this kind of enhanced value. And so Hindsight Replay has been an absolutely critical advance in making these more data efficient and learning harder tasks that involve a more complex state space. And it's much more what a human would do, right? Like maybe I'm playing tennis and I mess up, some aspect of hitting the ball, and it goes in a different direction than I thought. But maybe in the future, that's exactly what I'm going to want to do. And so I'm going to catalog that back. And when I need to do that in the future, I'm going to have used that information. So it's much more memory efficient. Reward efficient, sample efficient. Okay, good. So in this video, I've talked about reinforcement learning, which is a framework for learning from experience, how to interact with the environment. So in the next lecture, I'm going to talk about how to do this with neural networks and some of the really exciting advances in the field. All right, thank you.